This problem-solving video was created for High Point University physics students. You are doing rocket science, and it's a blast. In this problem, we want to calculate electric field due to a rod of length L that has a uniform charge Q. We will derive an expression for the electric field at point P that is on the axis of the rod and is at a distance d from the center of the rod. Also, we will show that in the limit, as d goes to infinity, the electric field due to the rod will be the same as if the rod is simply a charged particle at the origin. Let's define the origin x equals 0 to be the center of the rod. The positive x-axis will point to the right along the axis of the rod. That makes the left end of the rod at the location x equals negative L over 2, and the right end of the rod is at x equals positive L over 2. Now we have to break the rod into pieces, each piece with charge dq, and find the electric field due to each piece dq, and then add it up, that is, integrate. So let's sketch a piece of the rod dq. It has a width or length dx and is at the location x on the rod. The point P is at the location x equals d, and the electric field due to just the piece of the rod of charge dq is dE. The net electric field will be the sum of the electric fields contributed by each piece of the rod. Now the rod is uniformly charged. This means if you take the charge of a piece dq and divide by its length dx, that's the same as the overall charge divided by the overall length. So we can write the charge per unit length dq dx as q over L. Now let's find the electric field due to a single piece of the rod. We just use the electric field due to a point particle. It's 1 over 4 pi epsilon naught times the charge over the distance squared. The piece is located at the location x. Therefore the vector r from the piece to the point P will be the position of the point P minus the position of the piece. This is just the distance d minus x in the picture. It's easiest to recognize that this distance is just d minus x and that the unit vector will point in the x direction. This is important because the electric field is only in the x direction. Therefore, we can work with the x component of the electric field since the y and z components are 0. We must substitute for the charge of the piece of the rod in terms of the width of that piece of the rod. Because we will now calculate the net electric field by summing the contributions of the electric field of each piece of the rod. Our limits will be over the length of the rod from negative L over 2 to L over 2. Then you must integrate the quantity 1 over d minus x squared. You can use your calculator or substitution to do the integral. Remember that this is a definite integral, so you must substitute the limits of integration. Make sure that you keep track of those negative signs, and then simplify the expression. You must find a common denominator by multiplying the first fraction by d plus L over 2 over d plus L over 2, and the second fraction by d minus L over 2 over d minus L over 2. Then you can add the numerators because you have a common denominator. Distribute that negative sign over the second term, and you'll notice that your d's will cancel out. You'll be left with L over 2 plus L over 2 in the numerator, which is simply L. And this cancels with L in the denominator. Now let's write the magnitude of the electric field along the axis of the rod due to the charge on the rod. Because this is the magnitude of the electric field, it will depend on the magnitude of the charge of the rod. The direction of the electric field will be along the axis of the rod and will point away from a positively charged rod and will point toward a negatively charged rod. Now let's consider what happens if the point P is at a distance that is much greater than the length of the rod. In this case, the term L over 2 squared is much less than d squared and is therefore negligible. That leaves us with an electric field that is proportional to 1 over distance squared, and this is precisely the same relationship as the electric field due to a point particle. This problem-solving video, which hopefully gave you some bright ideas, was created with a High Point University Think Big grant. These grants encourage teachers and students to be innovative.